లేపోతే ఇప్పుడు కాదే. Okay, can someone confirm if they can hear me?
Yeah, we can hear you.
Okay, so we'll start now. So basically, compilation and assembly is all about how you can get a C program to get executed by a machine. So computers can't really understand instructions or programming languages and all that. So that's a process from which it's converted into something that a machine can understand. And the different steps that it has, starting with pre-processing. You might have noticed that there's comments in C that you can add with the double slash option. All of that is removed in this step. And then here in this example right here, we have something called hash define n5. This basically substitutes 5 wherever n is. So it substitutes all the text uh, with the capital N as 5. You might have seen this in some programs where they might be substituting pi with 3.14. You might not want to keep typing 3.14 over and over again, so you just add a macro definition in the beginning. So yeah, pre-processing has like all of these steps which prepare your program for compilation. So after that, it also includes all the header files, and header files are the files that define a lot of important functions like printf or scanf that you use regularly, but you don't really know how they work or what the code and the logic behind them is. But all you have to do is include these header files and you can use those functions. Okay, apart from that, pre-processing also includes conditional macros. Basically, if and if def, you can use them to check if something has been defined, and then you can set options where the program won't be compiled if those things aren't defined and all that. So outside of that, the next step would be compiling. So the file that you start off with is a .c file. And then after pre-processing, after all the macros are expanded and all the comments are removed and all header files are included, you end up with something that's now ready to undergo compilation. And it's a .i file. And after that, after you end up with this .i file, you will move on to the next step, which is compiling. So the pre-processed source code is translated into assembly in this case. There are some compiler optimizations that are also performed. Basically, your compiler might change some instructions and ensure that it gives you the same output, but it might do some more optimizations on them. Errors are raised whenever there's a syntax error, or maybe your return type that a function is giving you does not match the function definition. So all of these errors are raised during the compiling phase, and after that it's converted to assembly. We'll get to what assembly is in a while, but basically it's a low-level language that has like a very high correspondence rate with machine language. So it's very, very similar to machine language, but it's still human readable and you can understand what all the different instructions are. And yep, we'll get to assembly in a bit. So after that, the file that you end up with after the .i file is a .s file. And after that, you send it through an assembler. An assembler basically converts assembly code into machine code. So after this point, you can't really understand what this new file is going to say because it'll be all numbers and all binary instructions. Basically, you can't read it anymore. I mean, you can read it, but you won't understand it. Uh, and the file that you end up with in this stage is a .o file or an object file, basically. After this, so it's now your file is almost ready to be executed. There's some other things that still need to be done. Suppose you have two files that you're compiling together, and the definition for a function that you're using in one file is not included in the other file. So a linker's job is basically to include all these definitions, and also all your standard libraries. They have to all the all the functions out of these have to be resolved so that they can be used by your program. And that's basically what a linker does. It combines multiple object codes, object files into one final executable. And on Linux, you'll see that this executable is usually called a.out. But you can also, okay, so here there's a file that basically just adds n and 5, and n is being defined as 5. And you can compile this with the flag save temp. Ordinarily, all these pre-processed files, all the .i, .o, .s files, they're all thrown away because they're intermediate files. And the only thing that remains is basically the executable. So if you compile it with the flag save temps, all of the intermediate files are also saved. So you can take a look at your pre-processed file, your object file, your assembly file, all of it. And the .o, I mean the /o right here, it's a flag that's used to redirect your output into a file named compile in this case. So I told you it's usually directed to an executable called a.out. But this time compile.c, and you want the final executable to be sent to a file called compile. Okay, and now you can check all the various permissions in all of these files. You can see that compile.c, it does not have execute permissions because obviously it's basically text that humans can read, and a machine can't possibly execute it. So it does not have execute permissions. But finally, the executable that you produce after compiling, you can run it and it should say 10. If any of you want to try a simple program and try compiling it, and you want to look at all the various intermediate files that are produced in between, try doing that after the session. Um, okay, so pre-processed files, what were they again? They were basically files where all the definitions are substituted. Here you can see that n is still n here in the original file, but it's a macro definition. And here it's been substituted with 5. So that's your pre-processed file. It's already included the header file that's required for printf. And then after that, you come down to assembly code. Assembly is basically a language which all of your functions can be converted to this language. And it's very, very similar to machine code, as in it has a very high correspondence with machine code. So all code is converted to assembly before it's converted to machine code. And people can still debug and understand assembly. And here you can see all the various commands that are being used. You can look at move-l. You'll most likely run into move more often. The L stands for long. Basically signifies that whatever operands you're working on are 32-bit operands. And here in the object dump of the object file, you can look at all these numbers, the 55 foot push. You can look at the call instructions. You can look at move and move-l. All of these have now been converted to actual bytes, actual numbers, and actual like machine instructions. If someone told me that a certain area in your computer, certain memory spots said 8B 45FC, I wouldn't be able to tell that it was a move function. But that's what it is. It's all been converted to machine code. And finally, after that, linking is done and your executable is produced. Okay, now on to assembly. Assembly, like I've been telling you, is a language, is what the C program is first converted into. And it's still human readable. It's still, you can still understand what each of the instructions are doing. And to understand assembly, you still need a little bit more knowledge about the different registers that are used and what exactly every instruction is doing. But it's very easy to visualize this, as we'll see today. Computer architecture basically means since your machine code obviously depends on how your computer is built, the different specs, the CPU, the ALU, the registers, all of these combined make up your computer architecture. We'll get to what each of those are right now. Uh, so what I mean by instruction set architecture is you can have different types of, I'm not going to say assembly, but basically you can have different types of instructions and different design philosophies behind an ISA. So for most CISC systems, basically complex instruction set computers, what happens is that all of these, you have much more complicated instructions in assembly. They have, but on the contrary, for RISC systems, basically, you will have much more simpler instructions. Every instruction has a fixed length in RISC systems. It's a lot easier to decode. But because they're so simple and they can't perform, they can either save memory somewhere or they can add something. They can't do both. But you'll see that you can do both if you use a complex instruction set. So that's basically the difference between the two. Uh, Again, here you can see that the move instruction, it has multiple, I mean, it has a variable length. In the first one, there's 3 bytes corresponding to it. The second one, there's 2. In the third, there's 5. So it's a lot more complex to decode CISC instructions because they have variable length. They're a lot more complex in general, but they can also do a lot more than RISC instructions can. So yeah, that's the one we use in most of the laptops that you people use. They have x86, which is a complex instruction set. Okay. Okay, now on to what registers are. Registers, you can think of them, it would take a lot of time to it would take a lot of time if all memory had to be loaded up from the RAM and then processed by whatever instructions. So registers are basically high speed memory that are located in the ALU. I hope most of you know what ALU is. It's basically the place with all of these. It's the place where all programs are physically present, almost like. Um, so once a program is compiled, you'll have all these different sections for different types of variables and for different purposes. Basically, you'll have one section that's for local variables. You'll have one section that's for instructions. You'll have sections for global variables. You'll have sections for static variables and all that. So registers are basically they're storage elements that are very high speed. That's all you have to know about them. You can think of them as existing outside a stack. I'll get to what a stack is in some time. Okay, and then we have mnemonics for all of these assembly instructions. Um, we'll get to all the different functions in a while. You have add, you have sub, you have jump, ret. You'll also have push and pop, which are related to the stack. Um, okay. Okay, so in all of your new computers and laptops that come out, you might have what's called 64-bit architecture. What that means is the registers that are used have higher storage capacity. The x86 laptops basically have registers that are 32-bit. They can hold 32 bits. But now we have the 64-bit architecture. Obviously, it's backward compatible with 32-bit architecture. So all the programs that used to run on 32-bit computers can still run on 64-bit architecture computers. So in your 32-bit architecture, you'll have registers that are 32 bits long. So you have EAX, EBX, ECX, EDX, ESI, EDI, ESP, EBP. ESP and EBP are important because they basically point to they create stack frames. Again, we'll get to what that is in a while. EAX and EDX, you'll constantly see that they're used to basically perform a lot of data movement and all of that. ESI and EDI are used sometimes to pass arguments to a function and also for string operations. And in your 64-bit architecture, you'll have the very same registers. They'll now be replaced by RAX, RBX, RCX, RDX, RSI, RDI. And since they're backward compatible, in a 64-bit architecture, whenever you run a program that was initially for 32-bit computers, just the lower 32 bits of this whole RAX register will be used as EAX. Okay, so yep. Now we have to get to what a stack is. So you might have noticed that in a lot of programs, you often use you often use functions that you didn't code yourself. You might call functions like printf in your main function, but um, you haven't really written the code for them. You can also, especially in C, since C supports user-defined functions, so you can define functions outside of your main, and then you can call them inside your main. So you can kind of see this whole modular approach that comes up. Basically, even if you don't write the exact code for a function inside your main, you can call different functions, and different functions can call other functions within them, and so on. So you see this whole structure of some functions. Uh, you see this whole function. You see this structure where one function calls another. That function might call other functions, and there's a whole. One second. Okay, so in this example, you see that the main function is calling A, but it's not like after A is executed, you can just, there can be extra code written after A is executed. So after A is executed, you have to return to your main function. And within A, you see that A is calling a function B. But after B is done executing, you have to come back to A. So basically, you can call multiple functions, but um, you have to return to them. So how this is like physically done, and there's an analog in assembly. I mean, there's an analogous structure in assembly for this very purpose to support this whole modularity thing. First there's space allocated for main. There's a frame that's created for main itself, and all the instructions and all the local variables are decoded, and this frame is created. And after that, since it's calling a function a, there will be another frame created for a, after which a is calling b, and now there's another frame created for b. After b is done executing, this frame is basically uh, you return from this frame and you basically forget it's there. I mean, the memory that was used during the function, it's still there, but you just write over it again. So you can kind of forget that the frame for B is there after it's done executing. Okay, and then we see that A is calling another function C. So you write over that frame, you make another frame for C, after which C is done executing, and then you can return from C. And then you go back to A, you check if there's any other instructions left. If those are there, you execute them. And then finally, you return from A also. And finally, you return from main. So you can kind of see how if you have multiple functions and they're calling other functions, there's a framework that kind of establishes this whole thing where you can return from the function, and then you can go back to the previous function that was called. Basically, this whole approach is called the last in first out approach, because first the innermost function is executed, and then the flow of execution is returned to the previously called function. So in this case, you can see that first main is called, and then some function is called. And then after some function is called, there's a function called inner function that's called. And after this is done executing, it returns from it, and it returns back to some function. So innermost functions are executed first, and then the function that was called before it. You can kind of picture it the way you would picture a book stack. A bunch of functions are placed, and the very first book that you would take off the stack is the book that you placed there last. So, in a similar manner, the function that was called last is executed first, and then the functions that were called before that are executed after that. So it's called last in, first out because, again, it's similar to a book stack. The book on the top that you put in last goes out first when you pick it up. Again, it's important to note that a stack it's a physical place where place is made for local variables, and then as the function gets executed, you'll see this place being filled in with all the different values that you use during your function. There'll be user inputs that are filled in to the stack. So it's basically a physical place in memory. That and you create a new stack frame every time a new function is called. We'll see details on exactly how this happens. Okay, and there's another thing to note that stacks grow downward. So basically, in the example here, the frame for main is at a higher memory address, and then the frame for A and B and C, they are all at lower memory addresses. So you can start off at um, you start off at a higher memory address and you grow downwards. You grow towards lower memory addresses. Okay, now we go back to the two special registers that are basically used to keep track of where a stack is and how it grows. You have a register called the EVP, which keeps track of the base of a stack. And then you have a register called ESP, which keeps track of the topmost element of the stack. It's at the top of the stack. And okay, so when a program begins execution, the stack frame is created. Space is allocated on the stack for all the variables declared within the function. And then when main calls a new A is another function. A new stack frame is created for the variables in A on top of the main stack, basically at lower memory addresses. If A were to call any other additional functions like B or C, new stack frames would be allocated at the new top of the stack. And once these functions, once B and C are done executing, they return and you pop back into the previous stack frame. So here after B returns, you basically pop back into how the frame was before B was called. You pop back to the frame for A. There's something called a return address, which is used by the EIP. The EIP is basically an instruction pointer. Instructions are present in a different location in memory that we're not going to go into much depth about today. Today we'll mostly be understanding how the stack is built and exactly what happens and what instructions correspond to what. But basically, a return address tells tells the program where to go next, where to fetch the next instruction, and all these instructions are located in a different area. Okay. Up next, we have the different instructions in the x86 assembly language. You have move. Uh, Move is an instruction that basically copies the value from the second operand to the first. So move rex, rbx is going to take the value that is present in rbx, whatever data it has, and copy it into rax. And now after that, both of them have the same data. Uh, pop pop is interesting because it involves the stack, and every time you pop an element, the the RSP, which keeps track of where the top of the stack is. So if you pop it, like I said, stack frames grow from higher addresses to lower addresses. So if you remove an element, you basically go to a higher memory address. Like your RSP will go to a higher memory address because kind of you're forgetting that the element is there and it just gets overwritten when different programs are written, when other programs are executed. So pop removes the top element of the stack. And because you've removed this, it's also going to affect the RSP. The RSP is incremented every time you do a pop. So, okay, it removes the top element and it copies its value into the operand. So pop RDI is going to remove the top element of the stack and it's going to send it to the register RDI. And push is the exact opposite. It pushes the operand on top of the stack. So if there's an assembly instruction push rax, it takes whatever data is inside rax, it puts it on top of the stack. And because you've just added a new element to the stack, the RSP is now going to point to that new element, which means since the stack grew, the RSP decrements. So that's important to remember. Anytime you remove an element, the RSP is incremented because you're going back to a high address. Anytime an element is added, the RSP is decremented because you're adding a new element and you're going towards low memory addresses. Next up, we have load effective address. It basically takes the address of the second argument and it stores it in the first operand. So again here, LEARAX and val is going to take the value of val and place it in RAX. Uh, don't be too overwhelmed if you don't understand exactly what these instructions are. Once we move on to the actual visual image of how a stack works, this will make a lot more sense. Add adds the first and the second operand and stores the value in the first operand. So if I say add RAX comma 5, it basically adds 5 to whatever value was already stored in RAX and it'll save it in the first operand. So RAX value is changed from whatever it originally was to RAX plus 5. Uh, Integer subtraction, again, it does the same thing. It subtracts the second operand from the first and it stores the value in the first operand. You have increment and decrement. They, again, it's the same thing. They add one or subtract one to whatever element follows them. This D word pointer basically just means it's a 32-bit memory location. And XOR or these are all bitwise operations. I hope you know what XOR is. XOR basically returns 0 anytime. Okay, so 1 XOR 1 is 0 and 0 XOR 0 is 0. If you can look at the truth table, it's basically very similar to OR, except that 1 or, uh, 1 or 1 would give you 1, but 1 XOR 1 would give you 0. Okay, and okay, so for these bitwise operators, if you XOR two um, if you XOR two registers or memory locations, you basically just store the contents in the first operand. Another useful another use for XOR is it basically checks if two values are the same or not. Because if they were exactly the same, and 1 XOR 1 returns 0 and 0 XOR 0 returns 0. When you perform this bitwise operation with like a really long string of ones and zeros, if they're exactly the same, the XOR will return 0, 0, 0, whatever. Okay. And next we have some instructions which can control flow. Jump transfers program control to the location pointed by the operand. So jump to main plus 14 would jump to the 14th instruction from main. Jump if equal, jump if not equal. They're all based on compare. So compares values of the two registers. Will tell you if they're greater or not, greater, less than, or equal. And then you can. It's usually followed by these jump if equal, jump if not equal, jump if the last result was 0, jump if greater than, jump if greater than or equal to, jump if less than, jump if less than or equal to. So in the example, you basically compare EAX and EBX, and if these two are less than or equal, if EAX is less than or equal to EBX, it jumps to a location called done. Okay, wait. Call and ret, you will go more into detail, but these are basically call will establish something on top of a stack that's known as a return address. Uh, Basically, it sets up while setting up the stack, you push the return address onto the stack, and then the RSP is decremented because you just pushed another value onto it. And then the function that it was calling is then executed. And there's a setup for all of this. There's space allocated for the function that was called. And ret does the exact opposite thing. It allows the EIP to return to wherever the return address pointed to. So you'll go into a lot more detail about how these two functions work in coming sessions. But as of now, we'll just focus on how all of these different instructions translate uh, physically in a stack. For this, I'll be using the whiteboard. One second. Give me a second to set this up. Okay, one second. Okay, so basically on the left we have a C program that's doing something very simple. It has three integers. One of them is being initialized to 5. The other is being initialized to 10. And then there's a sum that's assigned the value of k plus L. So it'll be assigned the value 15, but we're making the computer do an addition here. And there's a printf, and it has two arguments. One of them is %d. This is called a format specifier. Basically, if it it tells you the data type of the argument that follows. So if I gave it for %p, or if I gave it %u, u is for unsigned integers, f is for floating point, or basically float, and then it basically specifies the data type of the variable that follows. And the second argument here is the sum, and that's the variable that needs to be printed. So the site that we've used for this is called God Bolt. You can go check this out. Uh, one second. Okay, so you can type very simple programs and you can look at all the different registers that are used during the program, and you can see all the different sections get highlighted, uh, basically telling you which instructions correspond to which line of code in C. Um, yeah, so you can type very simple programs and look at how it converts C to assembly, and you can look at all the different instructions and the different registers that are used and how exactly a stack frame is set up and all of that. You can go try this with simple programs on your own time. Right now, we'll try understanding exactly how a stack frame is set up. Okay, so here I have the same code which had integers k and l, and it was finding the sum of these two integers. we'll see exactly how this is done using a stack and how this is done done exactly with assembly instructions. Can Okay, so the very first operation, um, 1 second. I'm going to assume for the purpose of this that there's already a previously existing stack frame because I want to show you how exactly one function is called and it's how the stack frame is placed over the previous stack frame. So for the purpose of today, I'm going to assume that there was already a previously existing stack frame. So basically you have the previous stack frame, you have RBP and you have RSP. Uh, you'll remember that RSP points to the top of a stack and RBP points to the base. So this is your previous stack. Can someone confirm if it's visible or if it's
It's
can
visible.
can you see what's below RSP or should I
No.
draw to the side? Okay. Okay,
Yeah.
I'll draw to the side. 1 second. Okay, so I'm gonna assume that there was a previously existing stack frame. RBP points to the bottom of the stack and RSP points to the top of the stack. So basically here was your previous function stack frame. Stacks, again, I'm reminding you, they grow from higher memory locations to lower. So as we build, we go to a lower memory address. So after this, our first instruction is push RBP. Okay, this is not how it actually is. There's also a call instruction, which basically pushes the return address on top of the stack. So there's a return address here, and 1 second. Okay, and RSP is pointing to the top. Okay, so the very first instruction we have is push RBP. And I'll read the description for this instruction. You push basically pushes whatever value is in this operand on top of the stack. And because you've just pushed a new element into the stack, your RSP will get decremented because your RSP will get decremented. So now after you've pushed RBP onto the stack, you have your previous stack, you have your return address, and you have the value that was that RBP was pointing to. RBP basically points. I'll tell you why this is important in a bit. Basically, RBP was pointing to its old location, and for some reason, you're pushing that onto the stack. So now you also have saved RBP. You have saved RBP on the stack. You have the previous stack frame, you have return address, and you have saved RBP. And RSP, now that you've pushed a new element onto it, it's going to point to this new location. Okay. And after this, the next instruction is a move RBP RSP. So move, basically, it's supposed to move the contents of the second operand into the first operand. But in this case, what it actually does is your RBP points to this spot and your RSP is pointing to this spot. And the instruction move RBP, RSP basically makes RBP point to the spot which RSP was pointing to. So you have your previous stack frame, you have your return address. We push the value of RBP. So we have saved RBP. We've saved whatever old position it was in, or it's also called old RBP. And now the move RBP RSP instruction has basically made both RBP and RSP point to this spot. So both RBP and RSP are now pointing to the same spot. After that, our next instruction is RSP subtract RSP 16. Okay, so after we got to this, where RBP and RSP are pointing to the same, we have the instruction subtract RSP, 16. So it basically subtracts 16 from the pointer, which basically means I'm allotting space for all my local variables. Again, I have my previous stack frame. I have the return address. I have old RBP saved. RBP is now pointing to the old RBP. And now RSP, after you do subtract RSP, 16, RSP is going to go to a lower memory address because you're subtracting 16 from it. And let's just assume this is 16 bytes. RSP now points to the top of the stack, and you've allocated 16 bytes of space for all your local variables. Okay, now you've basically created a stack frame for your new function. Basically, for printf, for main, you've allotted 16 bytes of space. And the next few instructions are basically how the space gets filled with all the values. Uh, okay, so the next instruction we have is move. 1 second. The next instruction we have is move dword pointer or double word pointer at
It's not
RBP
fully
minus.
visible.
Okay, my bad. 1 second. Okay, so after you've allotted 16 bytes for your main function, the next instruction is move dword pointer RBP minus 4, comma 5. So again, you'll remember that move takes the second operand. In this case, it takes 5, and it moves it. Dword pointer basically symbolizes that it's a 32-bit location. Some of you might know that integers take up 4 bytes of 32 bits. So what it's saying is that at the location RBP minus 4, it has to store the integer value 5. So this basically changes the stack to, it changes the stack. Again, you have the previous stack frame, you have the return address, you have old RBP. Is my handwriting legible? I'm really sorry about this.
It's fine.
Okay. Okay. And RSP is pointing 16 bytes over this. RBP minus 4. Again, this stack grows from higher to lower locations. RBP minus 4 is a location over here. And the value we're storing inside is 5. Okay, and the next instruction is also exactly the same. It takes the value 10. The next instruction is move dword pointer RBP minus 8, RBP minus 8, comma 10. So it takes the value 10, it copies it into the location RBP minus 8. So this location here is RBP minus 8. And it now has the value 10. After this, we have two instructions which are used to add 5 and 10. Okay, so now your stack looks like this. There's the previous stack frame, there's ret, the return address, there's old RBP. 5 and 10 have been saved onto the stack. And after this, we have two new instructions. Move edx, comma, double word pointer at RBP minus 4. So what this instruction does is it takes the edx register and whatever value is at RBP minus 4, and in this case it's the value 5. It takes 5 and it stores it into edx. And the next instruction is move into EAX double word pointer RBP minus 8. So it goes to the location RBP minus 8. It sees the number 10 here and it moves it into EAX. So in EAX, there's now the value 10. And then the next instruction is add EAX, EDX. So what this does is it adds 5 and 10 and it stores the value in the first operand. So it stores the value 15 in EAX. After this, remember that EAX stores the number 15. The next instruction The next instruction says move the next instruction is move double word pointer at RBP minus 12, comma EAX. Again, this takes the value that's stored in the second operand, in this case EAX, and it moves it into the pointer at RBP minus 12. And the location RBP minus 12 is here, right below 10. And it takes the integer value 15 that's stored in EAX and it stores it over here. So, okay, we've basically filled our memory with all the integers and the sum of those, sum of 5 and 10. After that, the command that follows is, I have no idea why compilers do this, but there is, 1 second. Okay, so the next two instructions are move EAX double word pointer at RBP minus 12 and move ESI, comma EAX. So it takes the value at RBP minus 12, and in this case that's 15, and it moves it into EAX. And then after EAX has the value of 15, it moves this value 15 into another register called ESI. So ESI now has the value 15. After that, the next instruction is EDI, move, comma EDI, and it points to a location where, okay, so in this assembly over here, you can see that dot LC0 is a string, that saves the format parameter. It saves %d/n, \n. \n is the escape or the new line character. It creates a new line. And %d signifies that the operand that follows is an integer. So ESI now holds the value 15 and EDI, you've moved into EDI, the string %d \n. And after that, again, it says move EAX, 0, so EAX is made 0. And now it calls printf. For those of you that are familiar with the calling convention, EDI provides the first argument for printf in this case, and ESI provides the second argument. So EDI provides %d \n, and ESI provides 15. So printf knows what the format of the following variable is, and ESI gives it the value of an integer 15. And then printf does its thing. It prints 15 onto your screen. And then finally, we are undoing the stack frame because we've finished executing our main function. And now the next three instructions that follow are called function epilogue, which is basically you're undoing the stack frame you just created to do all this, to call printf, to add two numbers. you do a leave, which basically a leave is similar to 1 second. You basically the last three instructions are move EAX comma 0 and then a leave and then a ret. I'm not going to go into detail of what a ret is, but a leave is basically it's its own instruction, but you can also understand this and visualize this with two functions: move RSP. 1 second. Okay, a leave is equivalent to move RSP comma RBP and pop RBP. It's not internally doing this, but it's just what it's equivalent to. That basically means the machine code instructions aren't the same as a move followed by a pop. Leave is its own instruction, but you can compare it to move RSP comma RBP and pop RBP. So what does move RSP comma RBP do? Just like how in the beginning we had our stack, we had RBP pointing to the bottom of the previous stack and RSP pointing to the top, and we had the function move RBP comma RSP that basically brought RBP to the same location that RSP was pointing to. So RBP and RSP pointed to the same location after this. So again, we're doing the same thing. We move RSP comma RBP. So we take RSP and we move it to the location where RBP is. So uh, your stack now looks like this. RBP is here. RSP also points to the same location. That's what move RSP and RBP does. And then we have a function called pop. Again, if you look at the definition of the function, it takes whatever value is inside RBP and it moves it to RBP. And since RBP is pointing to its old value, if you move that value into RBP, if you pop RBP, that is, RBP will start pointing to the same location. It'll point to where old RBP was, which is at the bottom of the previous stack. So pop RBP basically makes RBP go back to its old RBP value. And then since you've popped an element, the stack should now, you've removed an element of the stack pointer should get incremented because you just removed an element. 1 second. Okay, so since you popped an element of the stack, your RSP is now going to show you um, the previous memory location. So it gets incremented. It basically goes to a higher address and it's back to pointing at the return address. And now the very last instruction left is ret. You learn what this function is exactly doing in a stack in upcoming sessions. But basically, since RSP is pointing to the return address, you know where the next instruction can be found. You basically load that value into the instruction pointer or EIP, and then you can continue you can go to the next instruction. So that's what ret does. And this is how your stack finally looks. You may have noticed that 16 bytes were allocated, but the local variables used only 12. Uh, that's for that's something called stack alignment, where you'll frequently see that there's some junk bytes that are just left in the stack because it's faster if you because for some compiler optimizations, it's faster if RSP is at some multiple of 16 offset from RBP. So that's why even though only 12 bytes were required, 16 were allocated while the stack was built. So that's about it. You just learned how a stack is created. You understood what each of the instructions do, and you also saw how it's returned to the previous stack. Now all of these numbers 5, 10, and 15, they basically just remain in the memory till they're overwritten by some other function's local variables. And that's it. Okay. Hopefully you understood what each of these instructions do, and you can try. Okay, I've written all of this in the slides also so that you can refer to them later. Okay. The function epilogue basically allocates space. Uh, the function prologue allocates space, and the function body, it does whatever it was supposed to do. It added 5 and 10, resulting in 15, and it stored it somewhere. And then that's your printf call. EDI gives it the first argument, %d. ESI gives it the second argument, 15. Um, and then your function epilogue, whatever space was allocated initially is now deallocated, and you're done. This is another example. This is a simple program, and this is the assembly instructions that follow it. I'll suggest you try to decipher what's happening, maybe draw a stack frame to understand exactly how each function is doing, is making the stack frame and doing all the operations. That ends the content for today. Uh, does anyone have any questions? Someone raise their hand. Um, you can unmute and speak. I've given you permission.
Uh,
Yes.
yeah, so for the people who have any doubts, just raise your hands. We'll unmute you one by one, and then you can ask your doubts. So, Lavish Sharma, I think you can unmute yourself.
Is there a
Mm,
specific part anyone wants me to repeat? Should I go through everything once more, summarize it? Okay.
okay, I think Lavish's hand was just raised before. So, Rishabh, go ahead, please.
Ma'am, what is the types of journal purpose registers? Can you explain?
Sorry, general type registers and what?
Ma'am, types of journal purpose register. Ma'am, I
Okay, so
joined the class late. So,
okay. You want to know what RAX, RBX, RCX, RDX, all of those are?
Yes, ma'am.
Okay. Okay, so generally you come across. One second, I'll present again. Okay, so this part,
Yes, ma'am.
they're just registers that hold all values. RSI and RDI are used sometimes during calling conventions. Like you just saw, printf, the very first argument was passed to it by EDI, and the second argument was passed by ESI. And they're also used for format-based functions. I mean, my bad, string-based functions. And ESP and EBP, and they're the same as RSP and RBP. They point to the top and the bottom of the stack. You'll come across the registers more and more, and you'll understand exactly what they do. But they're basically just high-speed memory. They hold data, or they point to a certain location in data. There's also the instruction pointer, EIP or RIP. It points to another section. It points to another section called the data segment, or the text segment, the code segment, basically.
Okay,
It
ma'am.
points to where all the instructions are.
Yes, ma'am.
My bad. It doesn't point to the data section. It points to the code or the text section. Data is different. Okay, Sanjay Sutar, I'll give you. You can unmute and speak.
Hello,
Yeah,
ma'am. Can you revise your complete PPT?
complete.
Ma'am, complete the PPT.
Okay, I can do that.
Uh, just end, Rohit. Before that, does anyone else have any specific doubts? Because this is going to take time. If you do, please raise your hands. Mm, okay, I think you're good to go, Rohita. Just do it.
Okay,
Okay. Wait.
okay.
So yeah, Lavish, you can go ahead and ask your doubt. Lavish, are you there? If not, the next person, 21F110, can go and start asking the doubt.
Yeah, sir. Last time you said that you would share this PPT and lecture recording session, but I don't find it anywhere.
Yeah. So regarding that, there's a minor hiccup. We'll post the recording soon. As for the PPT, we'll provide it. Actually, we'll do this. We'll provide the recordings for both these sessions together, and we'll provide the PPTs together as well. We will provide them. There
Okay.
was a minor technical hiccup from the BNE team, so sadly we couldn't.
Okay. Thank you.
Okay. Lavish, any doubts? Else I'll just lower your hand. Okay. Okay, Rohita, go ahead with the revision.
Okay. Okay. In the start, we basically covered exactly how C code is converted into machine code. He went through all the steps. Pre-processing removes comments. It removes comments, it expands all your definitions, expands macros, and then it includes your header files. And after that, we have compiling, which basically converts it into assembly code. You're now more familiar with what exactly assembly is, and you've seen how that program was converted into instructions in assembly. After compiling, there's assembling, which converts it into machine code. You can't understand this code; it's all numbers, and function calls are resolved. A symbol table is formed, which helps in linking. So finally, you went from a .c file, and after pre-processing, it became a .i file. After compiling, it became a .s file. Then after assembling, you get an object file or a .o file. After that, it's almost ready to be executed, except you have to link some files together and generate a final executable. That's what the linker does. So again, we went through this example where there was a hash define N5. It basically replaces, so during pre-processing, N is replaced by 5 anywhere it's found. We compile this using the flags save temps because it saves all the intermediate files that were created. And then we also redirected the output file. Instead of a.out, it's now the executable is now called compile. That's what the flag O does. And after that, we learned what assembly is, how it's a low level language that's very, very similar to machine language. So it's useful to learn exactly what a computer is doing through these assembly instructions. We can still read and understand what it does and all the different instructions. Computer architecture is basically everything that enables you to do all this. It includes the CPU, the registers, the cache, all of those. And your assembly is going to depend on how exactly your computer is built. 32-bit architectures and 64-bit are the most common ones that we come across. There are some differences in how they process some things. You will see that arguments are stored on the stack for 32-bit architectures. It's slightly different for 64. But 64 is still backward compatible with 32-bit architecture. What that means is some of the software that was made for x86 computers, it'll still run on X. It'll still run on 64-bit computers. But instead of having these registers, which instead of using the entire RAX register, you will just use the lower 32 bits of it, analogous to EX, basically. So we learned what the key differences between complex instruction sets are and reduced instruction sets are. We learned that one of these, for complex instruction sets, you'll have every instruction can have a variable length. They're usually more complicated to decode, but your entire program might be executed in lesser number of instructions because each instruction is very powerful. For reduced instruction set, you basically learn that every instruction has a fixed length. It's a lot easier, a lot faster to decode these, but you might have to end up, you basically end up using a greater number of instructions. They both have their own uses on where you can use these. The ones we use in everyday life, all of your laptops, they're based on x86 architecture. So that's the complex instruction set family. After this, we learned what exactly registers are. They're just locations in memory that can store data or that are used to point to a certain location. And we learned about the different mnemonics we have for all the assembly instructions. You learned about pop, you learned about push, you learned what move does. Okay. And these are the commonly used 8 registers: RAX, RBX, RCX, RDX, RSI, RDI, RSP, and RBP. RSI and RDI usually used for string functions. We saw that in printf, RDI was passing the first argument. Basically the format specifier, the %d, and RSI was passing the second argument, which was 15. So the format parameter tells printf what the data type of the variable that follows is, and then that's followed by the variable itself. We saw what RSP and RBP do. RBP points to the bottom of a stack. RSP points to the top of a stack. There's also the instruction pointer, or RIP, which points to actual instructions in the code segment. You learn what all the different segments are in other sessions. But basically the stack and the code are two different sections in memory. We learned exactly why we need a stack and what the whole logic behind it was. We saw how functions can call other functions within themselves, and the function that was called last. Again, in this case, some function was called. Sorry. Sorry. Okay. So we learned exactly what a stack is and why it's required. We learned that the function that was called last has to be executed first, and you have to return to the previously called function. So in this example, main, there's a frame for main, after which a frame for the function A is created. And when we go to A, we see that A is calling another function B. So there has to be a frame that's created for B. Once B is executed, you return from this. You basically deallocate whatever place was allocated when that frame was created, and then you go back to the frame for A. After that, after B is executed, you see that C is being called. So that's a frame that's made for C, and then you exit from C again. Not exit, you return from C and you again forget that there was a frame here. You go back to the frame for A, and then you finish executing A. So you return from A and you're left with your original frame for main. So what we see is that whatever function was called last had to be executed, and then you had to go to the function that was called previously. The approach is called last in, first out, because whatever function, again, whatever came last had to be executed first, and then you go back to the function that was called before that. So this is what roughly a stack will look like. It's growing from higher memory to lower memory. Space is allocated for functions that were called last, and then it's deallocated and it goes back to what it originally was. You have the EBP, which points to the bottom of the stack, and stack pointer, which points to the top of the stack. We learned that push and pop affect the stack pointer, because if you add an element to the stack pointer, if you add an element to the stack, the pointer will now point to a lower memory address because you just added an element. And EBP remains right there. It's usually used. You may have noticed that all the local variables were passed at some location, that is at some offset to the base pointer. So you saw that there was something being stored at RBP minus 4. There was another integer stored at RBP minus 8. So it's kind of used as a reference for where you can place all your variables and all your yeah, it's used as a reference basically. After this, there's a return address that'll be used to go to the next instruction in the code segment. And then we learned what move is, pop, push, load, effective address, add, subtract, increment, decrement. You learned what XOR is. You learned all of this. Call basically pushes the return address on top of a stack. Return gives the EIP, the instruction pointer, the next instruction it's supposed to go to. And then we went through an example. We saw a simple code here that has two integers, 5 and 10, and then it has another integer which is the sum of those two. And we called printf, and then we made it print the output of this function. Okay, so you saw how push RBP worked, how we saved the old value of the previous stack because we wanted to return to it. And we saw what move RBP and RSP do. They make both of them point to the top of the stack at the moment, which will soon. Okay, and then we allocated space for all the local variables. 16 bytes were allocated because you subtracted 16 from the RSP. And then the function body, we saw what that did. We stored the value 5 at a location RBP minus 4, 10 at a location RBP minus 8. And then we loaded these values into EDX and EAX. And the function add EAX comma EDX adds both of them and stores the value in EAX. So now after the add, EAX is going to have the value 15. The next instruction stored this value at the location RBP minus 12. Then we had a call to printf. We moved the value 15 into ESI, and we moved the string %d \n into EDI. And then we called printf, and we basically supplied its two arguments with ESI and EDI. And after printf is executed, we did a leave. A leave is equivalent to a move RSP, RBP and a pop RBP. Basically, it moves the stack pointer from the bottom where it was pointing, the top of the stack where it was pointing, back to the bottom. And then pop RBP loads the value that it's pointing to. So it loads the value of the old RBP. And now RBP is going to point where that is. And because you popped an element of the stack, RSP is going to get incremented. So from start to finish, you saw exactly how this was done using assembly instructions. The site that you can use to convert basic C programs into assembly and see which registers are used and all that is Godbolt. So play around with it, type some simple programs, see what happens. And that's all we had for today's session. Pragyan, I've allowed mic for you. Can you ask your question?
Hello?
Yeah.
Yeah, I just wanted to ask that what was that string growth and stack growth? So stack
Okay.
growth, I understood it was pointed downwards. What about the string growth?
Yes, yes. I'll explain that one part. Okay, so what he's talking about is this picture that says stack growth, string growth are in opposite directions. So whenever you have these functions printf or scanf, you give it a value at a lower memory address. I think I need the whiteboard for it. And once you pass the string to the function, it starts storing the values towards higher memory addresses. So to give you an example, one second, I'll start a whiteboard. Or did you understand what I meant by that?
Yeah, got it.
Okay, so it basically is in the opposite direction. You give it the start of the string, and the string grows towards higher memory
It's
addresses.
just that the instructions would be stored at the lower one and the values of the strings would be at the higher ones.
No, it just means that you start storing the string from lower and it goes towards higher. I'll give you an example. I think it'll become clearer if I. One second. Give me 1 second to share the board with you. Okay, so we saw the stack, the previous stack frame and all that. They were they started off from higher memory locations and went towards lower. So suppose in my program I give it a character array that's say 10 bytes long. And if I provide this as an argument to some string function, I will also pass the start of this string. So the start of the string is at some lower memory address, and as it gets filled upwards into the stack. So if I give it a string name, it's going to go from lower addresses towards higher ones. It'll store the first character and then the second and then the third. It grows towards higher memory addresses. So we've seen how stack growth is from high to low, and we've seen how string growth is from low to high. That's all. That's all it means. You give it this address. You give it the start of the string.
Okay.
Is that clear?
Yes.
Okay. I must. Are there any other doubts? Okay. Then I think I'll end the meet then.
Just a second. I hope Lavish is able to unmute himself now. Yeah, Lavish, if you have a doubt, please ask. preferably without the background noise. Yeah, I think it's not happening. So, Rohita, feel free to end the meeting. Thank you all for joining.
Okay. 1 second.